let's recapitulate what we have actually studied last time, right? So basically we started with the small signal analysis, right? In small signal analysis, basically what we have covered is to calculate the small signal voltages and current, right? Voltages and current. You need to be very careful with that one. So whenever you are asked to do the calculation with respect to, let's say, if there is a question in your exam saying that to calculate the gain of the amplifier, okay, gain of the amplifier. If something is mentioned in your question paper, remember that you have to perform the AC analysis. Hagodo? AC analysis. I will not directly say to perform the AC analysis in your test, exam nalo. The question would be, most probably the question would be, calculate the gain of the given circuit figure. Okay. So if something is similar mentioned in your exam, then what you have to do is, you need to remember is, we need to perform the AC analysis, right? So whenever you perform the AC analysis, there are two important two components, right? First is you have to always perform the DC analysis, right? You have to always perform the DC analysis. After getting the DC analysis, you will get the value of IC, right? You will get the value of IC and VCE, which will determine the stable point of your transistor, Q point, right? Q point. After determining that IC and VCE, then you will perform the AC analysis, right? So when you perform the AC analysis, one very important consideration you need to take into account is regarding the existence of your voltage sources, right? You always have to short circuit the DC sources, okay? DC sources. And when you do the AC analysis, only there will be AC sources. No DC sources will be there, okay? This should be the very important consideration you have to keep in mind. If you fail to keep in this mind, then all of your analysis of that particular circuit would be completely zero, okay? Completely zero. So I cannot mark you anything, okay? I can simply give you gongdo, right? I can simply give you gongdo, okay? So when you perform the DC analysis, short circuit all the AC current source, right? AC current source, no, AC voltage source, and open circuit the current source. And if there are some capacitor, just open the capacitor, right? So this thing you need to be very careful. If you fail to do this one, I'm very 100% sure that your analysis part would be very zero, okay, gongdo, okay? So we have done some calculation, that is how to calculate the, firstly we started with the IC, right? IC, which is governed by Gm times VBE, right? Where Gm is called as transconductance, which signifies the how much percentage of your voltage signal is being converted into the current source, right? Current source. The second parameter that we have calculated is your small letter IB, right? Small letter IB, which is governed by, what's the equation for the IB? Gm by beta, right? Gm by beta. Then we have calculated the IE, right? We have calculated the IE, where IE is governed by alpha divided by Gm, or Vm by Gm divided by alpha times VBE, right? VBE. So again, there are two important resistance offer at the each individual terminal, right? One terminal is resistant offer at the base and resistant offer at the emitter side. The resistant offer at the base is represented by R pi, which is governed by VBE divided by IB, or which is equivalent to R pi. R pi. What's the formula for IB? IB lo R pi. Yes, VB by IB. If you simplify that one, what you will get? beta by GM, ina? Beta by GM, ina? Huh? Yes? 1 plus beta, 1 plus beta IB is your RE. That is the relationship between your RE and R pi, right? R pi is equal to 1 plus beta RE, right? So I mean, what is the formula for R pi? Beta by GM. So very three important parameter that you need to remember. How to calculate small letter IC. Okay, remember this one. How to calculate GM, the transconductance, and how to calculate R pi. These are the three fundamental formula that you always have to remember to perform the AC analysis. If you fail to remember these three, you cannot do process with the AC analysis. Hagodo, please remember small letter IC, small letter R pi, and GM. Okay, if you can remember these three parameter, completely you can solve the any AC analysis. Okay, any AC analysis. And we also looked into some how to represent, right? How to represent your transistor in a equivalent signal model, right? Right? How to represent your transistor with a equivalent signal model, which is similar to what we have done for the high voltage, right? High voltage, right? So your circuit for the representation of your transistor in your small signal model is similar to this one, right? So there is a one resistor which is called as hybrid pi model, right? So there is a one current source which is given by Gm times VBE, and you have, this is your collector side, this is your emitter side, and this is your base side. This resistor is R pi, and the voltage across this is your VBE. Okay, VBE, right? Sometimes you may also see this this VBE can be represented as a V pi. Okay, maybe you will see in some textbook you might see this kind of circuit where your VBE is being represented by R pi. No, V pi plus or minus R pi plus or minus V pi GM V pi. So this is your collector side, this is your emitter side, and this is your base side. Okay, base side. So we can say your VBE is actually your V pi, right? VBE is equal to V pi, or if another say remember most VBE is equal to V pi. So remember these two representation, which is your hybrid pi model, is just a representation of this particular symbol of your transistor, BJT transistor, in a small signal. Okay, small signal. We are not representing any form of arm. Let's say if there is a one resistor over here, if there is a one resistor over here, we haven't included in this particular circuit for now. Okay, if you have to include, if you need to include this two, then this situation will change. Okay, this particular circuit will change. For now, we are just representing this symbol of your transistor, symbol of a transistor in which form? Small signal form. Okay, which is in the form of pi model, right? Hybrid pi model. Agree? So we can actually, so this is your I, small letter IB, right? And this is your small letter IC, and from here there will be I, small letter IE, right? IE. So we can actually calculate your IE, right? From here. If you see here, you can use KCL over here, right? I think I have given as a homework yesterday, right? So this is the direction of your small letter IB, and this is the direction of your small letter IC, and this is one node, right? One node. If you blindly write here, so this is it's coming like this, one current is coming like this, and one current is coming like this, and total current is going from here, right? That means if you represent, this is I1, this is I2, and this is, let's say, I3. If you apply KCL, then your total current I3 would be governed by I1 plus I2, right? I1 plus I2. If you if you use this analogy over here, right? If you use analogy over here, this would be your IE is equal to IB plus IC, right? IC. From DC analysis, we know your IE is equal to IC plus IB, right? IC plus IB, very same, right? Very same. So here you can also write IE is equal to 1 plus beta IB, right? 1 plus beta IB through DC analysis. Similarly, you can also represent 1 plus beta IB, right? IB. That means the current which is flowing through this emitter terminal, we should get the magnitude of this magnitude, right? 1 plus beta IB. Now we need to confirm, right? Through this circuit, through this representation, we need to confirm whether we are actually getting this value of current at this part or not, right? We are saying that this is equivalent to this one, right? This circuit is equivalent to this one. If this is equivalent to this one, we should be getting this value of current at the emitter side, right? Emitter side. So let's do this one. Let's do this one. Tobega. So IB, right? So what will be your IB? Yes. VBE by R pi. Yes, very good. Your IC is equal to, IE is equal to VBE divided by R pi plus current KCL, use PMT. From here, your current IB would be, so IC, right? IE, right? Yes, plus GM VBE. Why plus GM VBE? This is current source itself, right? IE is equal to IB plus IC, right? So how you calculate I, right? Current. V is equal to IR, right? So you calculate I is equal to V by R, right? In order to calculate the current IB, what's the voltage? The voltage is VBE. What's the resistor? Resistor is R pi. That means we can calculate IB by VBE divided by R pi, right? R pi plus your IC. IC, there is a current source, right? That means whatever current is being generated by that current source you will be getting at this point, right? So that is GM times VBE, right? GM times VBE. So we can do something here. We can do what? We can take common VBE, right? VBE, which is now 1 divided by R pi plus GM, right? GM. We can further simplify this one, right? You can further simplify. Now, if I want to take R pi, R pi now bani be watching. This would be VBE divided by R pi 1 plus GM times R pi, right? Right? So what is this? VBE by R pi is what? VBE by R pi is what? IB, right? IB 1 plus, how can we write GM or R pi? R pi is GM times R pi is beta over GM, right? This two will get cancelled, so that's why you will get, ultimately you are getting IE is equal to 1 plus beta IB. Now we can say that, this symbol which is equivalently represented over here, they are same, right? We are getting still IE is equal to 1 plus beta IB, right? Now instead of writing this all the time during the analysis part, AC analysis part, now instead of writing this part, now we can represent with this circuit, right? Right? We can represent with this circuit. That's why henceforth, when you do the AC analysis, we will always represent our transistor, BJT transistor, with this equivalent circuit. Agree? So we will represent all of our BJT symbol only in the AC analysis with this equivalent circuit, either this one or either this one. Hagodo, right? I can also represent with the GM right? I can also represent in terms of beta here. How can I represent in terms of beta? Another, your current is represented by GM times VBE, but most VBE, right? I can represent in terms of beta times something, right? Right? Maybe let's do this one. So GM times VBE, right? GM times VBE. So what is your VBE? VBE. IB, right? IB is equal to VBE divided by R pi, right? So we can also write VBE, right? VBE is equal to R pi times IB, right? IB, right? So I can write, so GM times VB is equal to R pi times IB, right? Right. I can write, right? So similarly, now I can also write R pi. R pi. How can I calculate R pi? R pi is equal to beta over GM, right? GM times beta over GM times IB, right? IB, right? These two will get cancelled. Now you will get, which is, that is GM times VB can be also equivalent to beta times IB, right? Beta times IB. Now in some textbook, the alternative way of representing this one, you can also see similar, you will also see similar to this circuit, okay? So you'll have collector, this is base, this is your ammeter. So this current can be also represented with beta times IB R pi plus or minus B pi. Hagodo? Hagui? In sometimes your hybrid pi model can be also represented by this part. Dachigi nalu dekashidu GM times VBE, right? GM times VBE. Instead of GM times VBE, I can also represent this current source with beta times IB. How we are getting beta times IB? We are just simplifying this particular equation, that is GM times VBE, right? I can write GM times VBE is equivalent to GM times, I can write VBE, right, from this equation. VBE is equivalent to R pi plus IB, right? R pi plus RB. So you represent this one, and then now we can also represent R pi. R pi is governed by beta divided by GM, right? Beta divided by GM. So if you substitute R pi, then this 2 GM get cancelled and you will get GM times VBE, which is also equivalent to beta times IB. Okay, these are the three configurations that you will see as the representation of hybrid pi model. Some textbook might represent with this particular current. Okay, in some textbook you will get this current source as beta times IB. Okay, IB. In some textbook you will see hardly this one, but some foreign textbook they use this one. Okay, they use this one. In most of the textbook you will dominantly see the circuit model of the small signal is either with this current GM times VB or this particular circuit. Okay, this two particular circuit. These are some exceptional case. Okay, in some case we may have to use beta to calculate your IC. In that scenario we may use beta times IB as a current representation in your collector side. Kosong. Now we are good to go to exercise. What? So this is done. This is done. Yes, this is also done. Yes, so this is one example to how to represent your circuit, right? So if you see here, if you observe this particular circuit, right? If you observe this particular circuit, I'm just representing only the AC part, okay? I'm only representing the AC part. Why? All the DC sources are being shorted, right? I can write the full circuit of this one, the circuit, full circuit before the application of your DC source would, AC source would be similar to this circuit. So this circuit I can also represent with this one, right? So before application of AC, this circuit would be similar to this one. So there is a AC source, then there should be a DC source, then it will go to ground, then it will go to your actual transistor. There is a resistor and there should be one VCC, then it will go to your ground, right? So we are taking V out from this part. So this is your RC, this is your VCC, this is your VBEB, and this is your small letter VS or VI. So this is your circuit, okay? This is a circuit before we apply the AC analysis. So when you do the AC analysis, this voltage source, right? All the DC sources will be short circuited, right? This will short circuited and it will be grounded. Because of this one, this will be reduced. And this is also DC source, right? VCC also DC source. And this will be also grounded. So this is the, you're seeing, this is the simplified version of your AC signal analysis, right? Now previously if you see, previously in this case, we are just representing this symbol of a transistor in your small signal, right? Now if you compare with this circuit, right? If you compare with this circuit, we still have RB, right? We still have RB. This is your RB. Now initially this circuit, right? This circuit and this circuit is just the representation of this part, right? Just the representation of this part. Now we have to include RC and RB, right? We need to include your RC and RB. And be very careful about the point we are taking your output, okay? So in this particular circuit, I am taking output at this point, right? I am taking output at this point, right? So if that means there is one connection from this point, right? One connection from this point. That means there will be one current going from here. That means one current will go there, one current will go there, right? That means your V out and RC is parallel, right? They are parallel. Why? I'm taking output at this point. Why? Here is a resistor, right? Going to the ground, and I'm taking output at this point. V out, that is plus or minus V out, right? So if you see here, there is one node, right? One node. There is one node. That means if something current is coming from this part of a current will go here and part of a current will go there, right? That means these 2 points, right? These 2 points are parallel to each other, right? Parallel to each other. That's why if you see here, if you see in this part, if I want to represent RC, that means your RC should be now parallel to this GM. Hagodo, this current source and this RC should be parallel. Why? Because of this condition. Okay, because of this condition, we are taking output at this point. Okay, we are taking output at this point. If one current is coming from this point, part of a current will go there, part of a current will go there. That means these two connections are parallel. That means this and this and this are all parallel, right? All parallel. Because of this one, when you represent over here, your RC is parallel, represented as a parallel to your current source. Okay. And there is most of the student tends to do mistake over here. Ani department. Oh, sorry. Hagudo, why we are representing RC as a parallel? And in the input side, In the input side, if you see here, this is actual input, right? This is actual input. That means your RB is series with the input, right? Your RB is series with the input. That's why if you see here, this is the input side, right? This is the input side of your transistor, right? This is the input side of a transistor. When you represent your RB, you are representing your RB series with the R pi input, okay? We don't have any parallel. Why? Your input part and your RB are series to each other. Series to each other. That's why there is a series of RB and R pi where there is a parallel connection between your current source and then the RC. Okay? This anidi system ka jago. If you fail to do this one, again your analysis will be wrong. Okay? If you represent series, then calculation will be completely different, right? Completely different. Now, if you see here, these two are parallel, right? These two are parallel. If these two are parallel, what will be the voltage level at this point and this point? Same, right? These two voltages will be same. Remember, anidi. Hagodo? So let's do this one. Let's do this one now. Besh. Now you have already understood, right? How to represent your small signal, right? Now try to represent this particular circuit in a small signal model. So this VCC is your DC source. V in, right? This small letter V in is your AC source, okay? This is your AC source and this is your AC output, okay? AC output. Remember, this is your DC. What kind of biasing is this one? Fixed biasing, right? Fixed biasing. Call somebody to do the representation of this particular. During AC analysis, what happened to your transistor? Okay. Directly do the AC baby, then try to model this kachulo transistor in a small signal model using hybrid pi model. Besh. Footballer, I will call you, okay? Where's Tandin? Tandin ni chara boni me. You have Tenzin, right? Yes, I will call for mechanical, okay? Randomly, mechanical, then electrical.
So there will be conceptually we know that there will be RE also in the model, not capacity.
No, the RE value is very low. So which is equivalent to 1. So the resistance offered by your RE would be very low. That's why we are not represent R pi, RE, small letter RE. But sometimes in design during the design, if they explicitly mention about the RE, then you have to represent the RE. RE, yeah, the resistance. Your current is, the total current will come at the emitter side, right? If the resistance offered by a emitter side is very large, if the resistance offered is very large, will you get any value of current? No, right? That's why we are not representing, right, the RE. That is a total current, right? Hakuimo. So during AC analysis, you have this DC source, right? This source, ground, right? It will ground, right? That means I can simplify that particular circuit. That is, I can represent like similar to this one. Your capacitor is during AC. It will act as a closed circuit, right? Closed circuit. That means it will allow AC to pass. It will block the DC, right? That's why it will short circuit, right? Right? It will allow your AC circuit to AC signal to pass, right? That's why it will try to short circuit. Now your DC source, and the DC source you what most. This DC source will short and it will be grounded because of this one. If you see here, your Vs signal source and your RB is parallel to each other, right? Parallel to each other. Similarly, this V out and your RC is parallel to each other. That means in this would be your changes there, right? This would be your RB and this would be your signal source, right? Right? And this would be the RC, then plus or minus V out. This would be the changes in your circuit, right? Dachi dilapchibate your RS, RB, right? Dachi case nalo. Where is that one? Aniki case nalo they are series, because if you see here, these two are series, right? These two are series. But with respect to this particular circuit is not same, right? It's not same as previous, right? These two are parallel, right? These two are parallel. Because of this one, there should be parallel between Vs and RB, and again your RPi and RB are parallel to each other, right? Right? That means what will be the value of voltage at this point, and at this point? Same, right? Same. I can say either VBE or VS, right? Either VBE or VS will be across this point, and this point. But the value of current would be different, right? The value of current would be different. So this is the way how you represent. Now he is asking very good question, right? We still have RE, right? We have RE, right? RE, the input resistance of at the emitter side, right? Emitter side. If you carefully observe this one, we are just representing your RPi, that is the resistance of at the base side, right? Input resistance of at the base side. We are not representing the resistance of at the emitter side. Why? IE is equal to IB plus IC. Now what is IE? IE is the total current due to IB and IC. That means we can say that is the output current we are getting from your system, right? Output current getting from the system. If this emitter, if you represent this emitter resistance, if the value of RE is very high, what will happen to your RE? You will not get RE there, most. You will not get IE there, right? Why? Because of this resistance, all of the current which is coming from IB and IC will be blocked. Right? What's the actual use of resistor? To control the flow of current, right? To control the flow of current. Now, if you represent RE over here, that means it is blocking some magnitude of current. That means we are not getting the full amount of current which are being supplied by your supplier, right? Source, right? Which is supplied by source. That's why we are not representing your RE. But sometimes during the design time, during the design time, some designer may include this RE. If they mention RE explicitly, then you have to consider the RE. But in most of the design case, we will not include your RE, okay? We will not include the RE. Reason behind is this part, okay? If your RE include, that means we are blocking some form of input current, right? That means we are not getting a good system, right? So remember, so this would be the changes in your circuit, right? Let's do next. Yes, do this one. This is your DC source. This is AC source, AC output. This you can do it, right? This you can do it. What kind of biasing this one? This is voltage divider, right? Voltage divider. Don't do the DC analysis, just do the AC analysis. So during AC analysis, now what will happen? Your R1 and R2 will parallel, right? Your R1 and R2 will act as a parallel. What will happen to this actual C1? C1 will short, right? Now everything will remain same, right? Come, you represent here. Yes, yes, Dhanin, Dalen, Tenzin. Yes. Minu Jojo, something Josh. Kala Tenzin show Tenzin. Yes. Chigi Benuzum Chi. Ana beta Tarigana. At here. Huh? I'm telling me, Kala Tandin. Tandin Shosh. Is this correct? Yes. Yes. Is this correct? Correct. Chu. It's very simple. Why? So during this AC analysis, this R1 and R2 will get parallel, right? There is RB, RS or RB, RS, right? RS, this R would be R1 parallel with your R2, right? R1 parallel to R2. Now if you see here, this is one node, right? This is one node. Why this is parallel? Why this parallel? So when it's AC analysis, this source, right? This DC source, right? This particular DC source will get grounded, right? This is the anime most R1, R2, right? R1, R2, right? This will be the simplified version of your this particular circuit in your AC, right? AC. Now, if you simplify this one, you'll end up getting this particular circuit, right? Right. Now, if you see here, this is your input side, right? This is the input side. So when this is input side, you look into the input side. This R1, R2, RS, they are all parallel to each other, right? Parallel to each other. That means I can represent R1 parallel to R2, then also RS parallel with R1 and R2, right? So I can write this two as a parallel circuit, right? Now in order to modify here, it's very simple, right? Very simple. Kachidu. This is the input side, right? In input side, you have R1 parallel to R2, right? So R1 parallel with your R2, and this R1 and R2 parallel to R2 are again parallel to your RS, right? You have now RS, then you have the actual AC source, right? VS. This would be the changes there, right? However, your output side will remain same. This is your just RC, right? Your output side will remain same. Membo. Why? We have more, okay? We have more. Now do this one. You see the changes in the circuit, okay? Here, in this part, again, this capacitor, right? This capacitor will short right here. It will short here, okay? It will short here. Now there is another form of circuit, right? This is very interesting. If you can do this one, I'll give you a thumbs up. That means you have fully understood what I have taught till this point of time. Now if you see here, we have one capacitor over here, right? one capacitor over here and one resistor over here, right? So now you have to make some changes over here, right? But the circuit will remain almost same. Use your brain now. Use your cognitive, right? Use your cognitive. This time I will bring who? Randomly, right? Randomly. I will bring one girl this time. Yes, analyze very carefully, okay? If you can analyze this circuit, I can guarantee you, you will definitely pass. You will definitely pass ECD 201. Okay? If you fail to analyze this one, I have doubt, okay? I have doubt. Just joking, okay? Just joking. You can pass, okay? You can pass. Remember this, from which point you are taking your output, okay? At which point you are taking at output, okay? If you do mistake over here, I'm again reminding you, you will get mistake, okay? Mistake in the analysis part. Yes, Pesh. So what will your circuit look like? All will remain same, but only you need to add one resistance over. Yes, you can explain to your friend. Come. Yes. I think you got your point. Yes, so sure. Yes, you are right. I got your point. Yes. Yes. Ano guys piyong lo? Yes, very good. Right. So during AC analysis, what will happen? This will short circuit, right? This will short circuit. So your current will come from here. Your current will always try to go from low resistance path, right? Low resistance path. If this is short, there is no resistance over at this arm, right? That means all of your IE will follow this path instead of your RE, meaning your circuit will remain same, right? Your circuit will remain same. So that's why you just need to put some cognitivity. Kasem thamidi tango semidani. Hagodo, right? Everything will remain same. Analung short chapchi minute, right? Another short chapchi. Another short chapdo. You see now, this circuit will look similar to this one. The most at emitter side, you have one resistor and one short, right? One short anyway, right? This would be the scenario in your emitter side, right? So your IE will come from here, right? IE, right? IE will come from here. That means all of your current will go from here, right? Go from here. The resistance here is high, right? Here there is low resistance, right? Zero resistance, right? That means all of your current will go through there. That's why your circuit will always remain same, right? Will remain same. Gutu la basic gutu, right? Gutu la mabawachinde ana map down me analu, okay? Okay, I can puzzle you, right? I can puzzle you, right? Right? Instead of going there, I can use here, right? 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 Ane twist bewachin dele shitsu kachbyong. Ane byong che, we say pressure increase shong dele. Right? Right? So your circuit will remain same, right? Your circuit will remain same as Anuzumbra remains same. Okay? Do you have time? No? Done. Right? So this is all about today. So please remember, okay? Please remember how to represent this one in AC analysis, okay? First and foremost thing is you need to remember this part, okay? You need to remember this part. After remembering this part, then you have to remember is how the if there are some resistors at the input side, how they are connected, right? How they are connected. For instance, analog chain, right? So during AC analysis, this will get grounded, right? This will get grounded, this will get grounded. Because of this one, this R1 and R2 and RS are parallel to each other, right? Parallel to each other. Or sometimes you may directly say, okay, you may say that you may say that I can do some modification, right? I can do some modification over here and say that series Zove, I can say series Zove, I will just say that R1 parallel with R2 parallel with your RS. I can also write similar to this one, right? Right? So remember, okay? First is, you need to always remember this part. Any part the Kadabi represent Beninata. Don't forget this point where you are taking your output. This will be always represented in your question paper, Nalu. This will be represented, okay, output. Sometimes I can also represent your output at this point. The pressure increase there, right? Right. I can also represent the output here, right? Pressure increase, right? Pressure increase. Sometimes I can also represent your output at this point, right? Output at this point. So you need to see possibilities of how I can give the question, right? But all of this circuit will remain same. You go to America, you go to India, you do the master's degree or PhD. This circuit will remain unabated. It will never change, okay? It will never change, okay? Remember, okay? So any doubt? No, right? I know, you know, say. Okay, yes, thank you.